Hello, my friends. Let me introduce myself. I am Professor James Edison, head of the Nuclear Physics Department. We are currently on board the Trans-Force spaceship, which is about to start out on an exciting journey into the world of nuclear energy. Today, we are going to talk about a very important issue: electrical energy. We will tell you how electrical energy is produced and how it is spent. You will learn how a power station is organized, what nuclear energy is, how a nuclear reactor operates, and you'll even get a chance to assemble it with your own hands. My assistant, Miss Jane Albright, who is a first-year student from the Energy and Environment Department, will be helping us on our journey.
Hello. Perhaps you already know what we need electrical energy for. TV sets, computers, and telephones use electricity as their power feed, the same way as we eat cereal and hamburgers. And if they don't get this power supply, they won't be able to work. Imagine what our life would be like. Computers not working, trams and metros stopped, and the food in the fridge going off.
In order to prevent this from happening, we need to constantly generate electrical energy and transmit it by wire to every house, every shop, every office, and even to every street lamp. Did you know that the amount of energy we consume every day is constantly increasing? Do you have any idea why this is happening?
This is quite easy to explain. We buy more and more computers, mobile phones, and household appliances. We open new cinemas, shopping centers, restaurants, and stadiums. Can you imagine? In some places, there's a shortage of electricity already. This shortage stops further construction as there is simply no energy to supply new buildings and factories.
Now, in order to get the energy we so desperately need, people use all different kinds of fuel. Fuel is the name that we give to the materials that can emit large amounts of energy. They can be found for the most part in nature and are extracted by industrial methods. In ancient times, there was only one type of fuel that people knew how to use, and that was wood. When they needed to heat their homes, to cook their food, or to get some light, they made fires and also fired their ovens.
But Professor, today, when our energy demand has grown so much, we can't only produce it from firewood.
Of course not. Today we also use coal, oil, and natural gas. Although those resources are limited, and as a result, the supply of oil, gas, and coal will someday come to an end. Now, because they can also be used to produce a lot of important things like medicine, fertilizers, and plastic, it would be daft and very wasteful to just burn them away.
And what do you think of sun and wind energy, Professor? Their natural resource is unlimited, isn't it? Power stations that work on sunlight or generate energy using the power of wind or sea tide can be built all around the world. They don't harm nature, and they don't use valuable fuel.
You are absolutely right. Solar and wind energy are completely inexhaustible. But today, the share of energy produced from these sources is relatively small, and it is not likely to increase in the future. Actually, in order to cover all our needs using the energy of sun and wind, we would have to fill large territories with solar cells and windmills and spend vast amounts of money doing so. Besides, even wind and solar stations can be harmful to the environment and bad for the population. They say that no energy is free, and that is absolutely correct.
There is one more source of energy: nuclear power stations. Building a nuclear power plant also requires a lot of time and money. On the other hand, the energy produced by it is much cheaper.
Well, let us find out what, in fact, energy actually is. During your physics lessons, you should have learned that energy is a capacity to perform work. We need energy for a car to start moving or for a kettle to boil. Now, there are several different types of energy. The sun gives us heat and light. This is called heat and light energy. Petrol burns in the engine and makes the car wheels rotate. This is called mechanical energy.
But most often when speaking of energy, we mean electrical energy. Electrical energy is the most widespread. Practically speaking, no single modern device or mechanism can operate without using electricity. People produce electricity using one and the same method. Heat energy, which emits from burning fuel, is transformed by means of a special device, a turbine, into electrical energy, which, in turn, is transmitted into our homes.
Energy cannot be seen, but it can be evaluated and measured. The most common measuring unit for energy is a kilowatt hour. Our electricity companies charge us for the amount of kilowatt hours we use each and every month. 1 kilowatt hour is consumed by a vacuum cleaner in 2 hours, by a computer in 3 hours, and by a TV in 12 hours. That same kilowatt hour will help us to charge the mobile phones of every student in the class. So, can you now see just how much electricity we need every day?
Well, you see, a lot of energy is used worldwide by quite ordinary people on their usual household needs. Our TV sets, refrigerators, and washing machines consume almost as much electricity as all the factories in the world.
You can quickly see that we are going to need more and more electricity year after year. An effective solution to the energy problem could come from the nuclear energy industry. Did you know, only 50 years ago, nuclear power stations were producing less than 1% of all energy generated in the world? Today, this figure has risen to 15%, and it will continue to increase well into the future.
Nuclear power engineering develops the most in the industrially advanced countries where very few power resources are left. For example, in European countries, between 20 and 50% of power is produced by the nuclear power stations. This means that if all of a sudden the nuclear power stations stopped operating, an average of 1 in every 6 lamps in the world would stop glowing, and half of all of the lamps in some areas.
In order to produce electrical energy, all kinds of fuel are used. Fuel is also the name given to the material which is used in nuclear reactors. And most often, this is uranium. Compared to other types of fuel, nuclear material is the most economical and the most effective. 1 kilogram of enriched uranium can give as much energy as one can get from 2 wagons of coal or 2 tanks of oil.
Thank you, Professor. That's very impressive. Let us take as an example a power station which is producing 1 million kilowatt hours of energy every hour. The calculations demonstrate that such a power station requires either 3 million tons of coal or 30 tons of nuclear fuel per year. In the first case, the station needs to be supplied with 5 trains of coal per day. In the second case, several wagons of nuclear fuel per year will be enough. Now you see how much energy nuclear fuel really has.
Now, another big advantage of nuclear fuel is its quantity. The reserves of oil, gas, and coal are coming to an end, while the reserves of nuclear fuel may last for thousands of years to come. Another bonus is that nuclear fuel isn't just used once. It can be reprocessed over and over again. That is why those countries concerned with preserving their natural resources tend to use quite a lot of nuclear energy.
In order to produce energy from coal, oil, or gas, it is necessary to burn them. During that process, clouds of black smoke and harmful wastes, including radioactive ones, rise up into the air. At nuclear power stations, all harmful and dangerous substances remain inside the fuel itself. They are not released into the environment. Even the hydropower industry has environmental problems. In order to build a hydropower station, vast territories need to be flooded. This leads to dangerous climate change and to the death of plants and animals.
And now, I think it's time for a game. That's right. Our onboard computer will now display the game on the communication monitors for you. Nuclear reactors and nuclear power stations are complicated engineering structures. In contrast to coal, it's not possible to simply dig uranium out of the ground, burn it in a furnace, and get electricity. The process of producing nuclear energy consists of several stages and is called the nuclear fuel cycle.
At the first stage, uranium is mined and then delivered to the plant. There, the uranium is processed and uranium fuel is made. And this is then delivered to the nuclear power station. At the next stage, the fuel is used in the nuclear reactor to generate electricity. Up to this point, the work of a nuclear power station doesn't differ much from the cycle of other power stations. But further on, there comes a difference. At the final stage, used fuel is not thrown out like ash from coal, but is packed into special containers and sent for temporary storage.
So, what happens to these containers afterwards? Today, in most countries, an open nuclear fuel cycle is applied, which means that used nuclear fuel is stored in special fuel storage pools. However, in the future, a closed nuclear fuel cycle will take precedent. It means that spent fuel could be reprocessed and used for energy generation all over again. Actually, this process could be compared to recycling of waste paper or of scrap metal. Even today, the technology for reprocessing used fuel is already being used around the world, and reactors that are able to use such fuel are being made. These technologies will make nuclear power engineering even safer and even less harmful to the ecology of the planet and to its people.
Let us take a closer look at how nuclear fuel is produced. The very first step to nuclear energy generation is mining of uranium ore. Uranium is the central element of nuclear fuel. By the way, you can find uranium in small amounts in any geological formation, in coal or granite, for example. So you have contact with uranium every day if you go up or down a granite staircase.
Usually, ore extraction is done in a pit or a mine. Recently, uranium extraction specialists have developed a method of underground leaching, which is considered to be the most ecologically clean. Well, unfortunately, uranium ore contains very little pure uranium, often less than 1%. In order to extract at least 1 kilogram of natural uranium, it is necessary to process tons of ore. After processing, uranium is ready to be enriched.
There is something I'd just like to add. Uranium enrichment has nothing to do with money. It is actually to do with the fact that natural uranium consists of different isotopes. Isotopes are variations of one chemical element that differ by atomic mass. For nuclear power production, only one type of atoms can be used: uranium-235. But this particular isotope is found in natural uranium in very little concentration, less than 1%. In order to make nuclear fuel, the concentration of this isotope should be increased to at least 3 or 5%. And this very operation...
This sorting is done with the use of centrifuges. A centrifuge is a device with a rapidly rotating drum, which is quite similar to that used in a washing machine. When a centrifuge is rotating at high speeds, the streams of uranium gas are driven round in a circle. The heavier isotopes remain near the walls of the centrifuge, and the lighter ones concentrate by the cylinder axis. The centrifuge is rotating at a fantastically high speed, an incredible 1,000 revolutions per second. If we decide to switch off the centrifuge's engine, it won't stop for 2 months.
During the uranium enrichment process, this separation is done thousands of times. Enrichment plants have not just 1 or 10 centrifuges, but hundreds of thousands, which means these nuclear plants can be 1 kilometer long. If we continue with our analogy with washing machines, imagine a gigantic laundry room with millions of washing machines in it.
At the next stage, the enriched uranium is then turned into a powder. This powder is used to produce uranium pellets, and it is in the form of these pellets that uranium is put into the nuclear reactor. Now, one uranium pellet, which only weighs approximately 20 grams and which is less than a thimble in diameter, can give off as much energy as we get from burning 3 barrels of petrol or 700 kilograms of coal. Now, 5 of these pellets would be enough to heat your home for an entire year. It's clear that 1 uranium pellet is too little to provide a full load to the reactor of a nuclear power station. In the energy generation process, thousands of pellets are being used at the very same time. So you can imagine just how much energy the nuclear reactor generates.
Uranium pellets cannot be poured into a reactor like oatmeal into a porridge pot. Finished pellets are put into a metal tube. This tube is called a fuel rod, or abbreviated to FR. In order to be loaded into a reactor, several dozen fuel rods are grouped together. And this group of fuel rods is called a fuel assembly. It is in the form of fuel assemblies that nuclear fuel is loaded into nuclear power station reactors.
Fuel assemblies are transported from the plant to nuclear power stations using special trains to avoid any potential problems or accidents. Generally, the reactor is loaded with 100 tons of nuclear fuel. After being loaded, fuel assemblies go on to provide energy for several years, after which time this fuel needs to be replaced with fresh fuel.
Okay guys, I think it's time for you to take a short break and answer a few questions. I really hope that having listened to this story, you won't find them difficult at all.
Members of the crew, please answer the quiz displaying the task on communication monitors. The time is over. I begin processing the results. Displaying the quiz results on communication monitors.
Okay, so now we can find out how the nuclear power station works. The principle of operation of a nuclear reactor is really very simple. It turns water into steam like any ordinary boiler does. The only difference between the two is that rather than using electricity or fire, the water is heated with the energy which is derived from the fission of uranium atoms. Despite this simple description, a nuclear power station is a very, very complicated engineering structure, and it uses the world's most advanced technologies. Usually in one station, there are several reactors working at the same time. Each reactor, together with its steam generator and a turbine, make up one power unit. One nuclear power station consists of several power units in a group of buildings that can occupy an area covering several hectares.
At the heart of a nuclear power station is a nuclear reactor. After fuel is loaded, a chain reaction begins. During this chain reaction, free neutrons split the atomic nucleus of uranium. In this process, the power that was being used to hold the particles of the nucleus together is released.
Power is an enormous source of energy, which heats the water in the reactor and turns it into vapor. In the process of splitting the uranium atoms, new neutrons are released. These neutrons continue this reaction over and over again until all the fuel is finished. That is why the reaction of splitting of atoms of uranium is called a chain reaction, because it keeps on going. During this process, the uranium nucleus is permitted to be split the exact amount necessary for energy generation. A self-propagated number, no more and no less.
In order to control the nuclear reaction, there are special rods. If these control rods are put down into a reactor, the reaction will stop altogether. These systems allow very precise control of the chain reaction in the reactor, and, if needed, they have the power to completely stop it.
5 to 7 years on, and this fresh fuel turns into irradiated or spent fuel, at which point it has to be unloaded from the reactor. It is very radioactive at this stage, which is why before sending it to reprocessing, the spent fuel is placed into a special cooling pond, where it is left to cool down. Later on, irradiated fuel is placed into a special high-strength container and sent for reprocessing or storage. The train which carries these containers takes a special route under tightened security. In the world's history, in over 50 years of this practice taking place, there has never been any emergency situation which would ultimately cause the release of radioactivity into the environment. Let's have a short break. Our onboard computer will now display a game on your communication screens.
Professor, many people think of radiation as a dangerous phenomenon that is threatening human life. I think people have this attitude because radiation cannot be seen and its influence is invisible.
Please don't forget that radiation is a natural phenomenon, just like sunlight or the Earth's magnetic field. Even human beings have small nuclear radiation. There are radioactive elements in the tissues of the human body, and to get rid of them is impossible. In fact, we receive radiation in small doses every day while eating, but nobody has stopped having their breakfast or dinner.
Professor, does it mean that radiation appeared long before people even created nuclear power stations?
Of course it did. Natural radiation has existed for billions of years and is present almost everywhere. We can't influence it, just like we can't influence earthquakes or the rising and setting of the sun. Scientists calculate that we receive 2/3 of radiation from natural sources, and the most powerful of these is the natural gas radon. The rest of the radiation we receive comes from having an X-ray examination or being on board an airplane. However, there is also radiation received due to human activity, which includes the radiation from nuclear power stations.
Does that mean that the people who live near the nuclear power stations receive more radiation than the rest of us?
In general, we can say that the share of radiation people get due to the work of nuclear power stations is very small. One should remember that radiation is harmless and even healthy in small doses. Of course, in large quantities, it can be dangerous. It is the same with fire, which can first bring warmth and then may burn if we don't move away soon enough. Radiation becomes dangerous when its intensity exceeds 60 microrenchen per hour.
Until recently, it was considered that nuclear energy would soon entirely replace all other energy sources. Unfortunately, after the Chernobyl accident, the development of nuclear power slowed down considerably. The accident at Chernobyl Nuclear Power Station happened on April 26, 1986, and is the most well-known incident in the history of nuclear energy. The main reason for this accident was errors made by the employees.
After this terrible accident, a large amount of safety improvement work was done at nuclear power stations. As a result of this work, the probability of accidents has been reduced by 1,000%. Nowadays, the operation of reactors has become so smooth that security systems are more focused on preventing someone from interfering with the operation of a reactor, either accidentally or deliberately.
Professor, is it true that nuclear power stations are constantly emitting radiation, even when they are operating in normal mode?
Actually, nuclear power stations are constantly emitting radiation, but thankfully, this radiation cannot spread beyond the reactor core. In order to prevent radiation emissions from spreading outside the reactor, nuclear power stations have a multi-layer protection system, and this is very similar to the traditional Russian Matryoshka doll in its structure. The first, very small Matryoshka is the fuel pellet, which has the uranium inside. The pellets in their turn are put into metal fuel rods. These are then put into the body of the reactor and a pipeline system which forms the next protective barrier. Finally, and this is now the largest Matryoshka, is a protective shell made of solid, thick, reinforced concrete. If ever a dangerous situation occurs, special rods are put down into the fuel inside the reactor, which stops a chain reaction and avoids any potential issues. Today, all security systems of nuclear power stations operate automatically under computer control and without human participation. Dear friends, I certainly hope I have answered all of your questions. So, now let me ask you some questions. I promise they won't be too difficult. Right now, the onboard computer will display them on communication screens.
Members of the crew, please answer the quiz displaying the task on communication monitors. The time is over. I begin processing the results. Displaying the quiz results on communication monitors.
Nowadays, nuclear energy is most often used to generate electricity. But in fact, the possible applications of nuclear power engineering are innumerable. Professor, could you tell us in what other ways nuclear reactors can be used now?
There are lots of other ways they are used, but you already know of one application, and that is nuclear icebreakers, cruisers, and submarines. Instead of having a normal engine, a miniature nuclear reactor is installed, which provides the energy needed for the motion required by the vessel. The quantity of nuclear fuel created is sufficient to keep these vessels operating continuously for several years. And just think, if this reactor were to be installed not on a ship but on a mobile platform, then we have an offshore nuclear power station. Such stations can be used for heat and electricity generation and also for seawater conversion. Just think that such stations can work without refueling for 10 to 15 years.
Scientists have recently developed technology that produces hydrogen with the use of new generation reactors. This method is much more effective and environmentally safe compared to traditional chemical methods. The process uses a high-temperature gas-cooled reactor, which enables the production of hydrogen and electricity at the same time. By the way, when the world's oil supply runs out, hydrogen could become the fuel of cars of the future, and you may well have the chance to drive them.
Hopefully, you have now understood how important nuclear energy is on our planet. But people won't necessarily be staying here on Earth. Very soon, nuclear energy will be needed out in space as well. But it can only be generated by nuclear plants, which are widely used in space already. I don't think you've had a chance to assemble a nuclear reactor before, and on our journey, it is quite a realistic possibility. So, who is going to assemble the reactor first?
Professor, we have already heard that it is necessary for us to find new sources of energy to supply the whole world in the future. Coal, oil, and gas need to be conserved and spared for use only when no other practical options are available. Nuclear generating technologies can only be used successfully to produce heat and electricity. What is our outlook for the future?
Today, nuclear power engineering is on the increase. Even those countries that scaled down their nuclear power sectors several years ago are returning to building nuclear power stations. In the next 10 years, more than 50 nuclear power generating units will be built worldwide. According to the International Atomic Energy Agency's forecast, by the year 2030, the total power of all the nuclear stations on the planet will grow by at least 40% and will come to more than 500 gigawatts, while alternative estimates suggest we could see a doubling of this total power, up to 810 gigawatts.
Thank you for your story, Professor. I hope you have all discovered a lot of new facts today. Now you know that radioactivity is a natural phenomenon and that nuclear energy resources can last for many years. The future of our planet depends on all of you. But one thing is abundantly clear. Using nuclear energy can provide the Earth with plentiful and stable sources of light and heat for many years to come.
Dear friends, let me say goodbye and thank you for your attention.